Hello everyone, I'm Xiaojian from Tsinghua University. Today I will present our work Max Multicore-Accelerated File System for Flash Storage. Modern storage delivers higher bandwidth. An off-the-shelf NVMe SSD can provide 5 GB per second write bandwidth. The bottom table shows the sequential and random bandwidth of flash-based SSDs that were introduced over the past 7 years. We observe that flash-based SSDs provide higher sequential write bandwidth. The ever-increasing bandwidth of SSDs motivates us to revisit the storage systems. This picture presents a traditional storage system. The host connects the storage device via a SATA interface. In the traditional system, the device can be easily driven by a single CPU. I/O is the bottleneck. Over the past decade, SSDs had gradually replaced the HDD. To better utilize the SSDs, the storage protocol was replaced with an NVMe interface atop the faster PCIe link. However, prior studies and we observed that the SSDs are underutilized. The CPU or the system software become the bottlenecks instead. A straightforward way to drive high-performance SSDs is to employ multicore CPUs to the system software. Here, we directly deploy existing Linux file systems atop multicore CPUs and high-performance SSDs to see why the system software benefit from more computing resources. During the evaluation, we launch up to 72 processes which perform concurrent I/Os repeatedly. We use the ideal setup to refer to the ideal performance of Linux file systems. In the ideal setup, we partition the drive and run an independent F2FS atop each logic partition. The left picture presents the throughput of file systems atop a SATA SSD. We find that existing Linux file systems scale relatively well on a SATA SSD. We conduct the same test on a NVMe SSD. However, we observe that most Linux file systems fail to scale for high-performance SSDs. Now, we analyze the system software to identify the root causes. In the hardware layer, the NVMe SSD has high internal data parallelism. The upper NVMe driver and multi-queue block layer provide multicore-friendly design to reduce the CPU contention from different cores. Applications can also issue concurrent I/Os to fully utilize the multicore CPUs. So, we presume that the file system becomes the scalability bottleneck. We further analyze the design of the file system. Here, we use F2FS, an existing log-structured file system designed for flash-based SSD, as an example. We decompose F2FS into 3 layers based on the functionality. In the concurrency control layer, multiple concurrent I/Os compete for a global read-write log to get access to the file system. Next, at the in-memory data structure layer, they sequentially update the in-memory data structures. Finally, they allocate space from a single log and are serially sent to the storage devices. Through analysis, we find that the CPU becomes the bottleneck, making the I/O devices underutilized. To address the aforementioned issues, we propose Max, a log-structured file system optimized for multicore CPUs and high-performance flash storage. The key idea of Max is to use sharding techniques to reduce the log contention, thereby providing higher CPU efficiency and I/O utilization. First, a read pass-through semaphore is proposed at the concurrency control layer to enable application IOs to enter the max in parallel. Second, max introduces file cell to partition and reorganize the embedded structure, enabling the IOs to access the indexes and cache with higher concurrency. Third, max divides the drive space into multiple independent logs and distributes complete file operations to each M log to achieve parallel persistency while ensuring consistency. We first introduce the concurrency control. In log-structured file systems, file operations can be classified into two categories: use operations and internal operations. Use operations can be roughly divided into read and write operations. These two kinds of operations are controlled by file-level read-write logs. The concurrency of the internal checkpoint and write operations are controlled by a global read-write log. The global read-write log keeps track of the number of readers and writers through a shared counter. As the checkpoint needs a quiescent file system image, it requires an exclusive mode log, which increases the counter value by a very large number. In a multi-core environment, the shared counter is then broadcasted to other cores. As the write operations may update disjoint parts of the file system in parallel, it requires a shared mode log. A shared mode log adds the counter value by 1 and then broadcasts the new value. However, the cache coherence traffic can be expensive for write operations. We propose read pass-through semaphore (RPS) to make the concurrency control of mass efficient. The key idea is to use per-core counters to avoid the cache coherence traffic in the common case, and leverage the CPU scheduler to check the per-core counters with low overhead. Concurrent writes only need to update its local counter without cache coherence. However, a checkpoint needs to check all counters to see if any writes are modifying the file system. One way is to aggressively plot the counter on each core. This kind of method achieves low latency, but may interfere other cores due to the inter-process interrupt. The other way is lazy wait, which waits for a condition that all cores have done a context switch and execute a full memory barrier. This kind of method is likely to introduce high latency due to the million-second scale ticket preemption, slowing the checkpoint. The RPS leverages the CPU scheduler to assist the log in checking the counter value, and uses periodic polling to make the checkpoint latency consistent with modern SSD's latency. The file system in kernel space frequently triggers CPU scheduler. RPS leverages this feature to track the counter values efficiently, thereby taking the free rides of the scheduler. For example, a write gets a shared mode log on core 0 and starts to execute. Then a checkpoint on core n is performed, is blocked, and waits for on-counter value reduced to 0. Next, the following write on core 1 is thus blocked. So when can a checkpoint execute? The first case is the normal CPU schedule on core 1. It notifies core n that no writes are in the critical section. The second case is when the write on core 0 completes. The scheduler is triggered and wakes up the checkpoint. Receiving notifications from all cores, the checkpoint can start to execute. Max introduces file cell to partition and reorganize the embedded structure. Max divides the file cells into multiple groups and indexes each group using a radius tree. Each file cell packs the inode table, inode, and file data, which are frequently accessed by a file operation. For file operations that do not modify the index structure, such as write, it first locks the group in shared mode, then locks the file cell of the target file before performing operations. For file operations that may alter the index structure, it locks the group in exclusive mode and then locks multiple file cells of target files and directory before executing. Max introduces mlock to scale persistence functions. The key idea is to divide the drive space into multiple logs. Each serves for atomic file operations. Specifically, Max dispatches atomic file operations in a round-robin fashion. Each mlog maintains its internal consistency, as in a single log, thereby keeping the consistency of atomic operations. The issue is how to keep consistency over multiple mlogs, as the file can be distributed to different mlogs. Max uses a global version number in each file's inode to decide the persistence ordering during crash recovery. Evaluation. The evaluation is performed in a 72-core machine and an NVMe SSD. We compare Max with classic file systems such as EST4, the baseline F2FS, and a recently proposed multi-core file system, SpanFS. We first report the results of data and metadata scalability. The x-axis shows the number of threads that issue parallel file operations, and the y-axis shows the throughput. We can see that Max achieves nearly 56 times speed up for data overrides. We also conduct the test on parallel create operations. From the figure, we found that Max achieves 2.8 times higher performance than SpanFS and 18.6 times higher than F2FS. We then report the results of applications. The left figure shows the throughput of the file bench file mail with varying the number of threads. We observe that Max achieves 2.9 times the throughput of SpanFS and 2.1 times the throughput of F2FS. The right picture plots the result of the logcb override, which pulls a 8 kilobytes value and frequently triggers compaction. The x-axis shows the number of threads performing compactions. We find that Max performs comparably against SpanFS and outperforms F2FS by 1.5 times. Finally, we study Max performance if the underlying storage has a sufficiently large bandwidth. We compare Max memory against a memory-based TempFS. We disable fsync and page cache flushes of Max to avoid duplicate on-disk copy, and refer to this setup as Max memory. We find that for data append write and metadata create operations, the throughput of Max memory comes close to TempFS. This indicates that Max scalability on these file operations is bounded by the VFS instead. To sum up, we present Max, a multicore-accelerated file system for flash storage to efficiently utilize multi-cores and high-performance drives. Using experiments, we demonstrate that Max performs significantly better than existing Linux file systems. That's all. Thank you.